In this video, we're going to finish Chapter 3. We're going to go through Section 3.11, Hyperbolic Functions. Certain even and odd combinations of the exponential functions e to the x and e to the minus x arise so frequently in mathematics and its applications that they deserve to be given special names. Okay, so the idea is, if we come to the definition of hyperbolic functions, this e to the x minus e to the minus x divided by 2 and e to the x plus e to the minus x divided by 2. These were found to occur so frequently in math that they were given their own special name. And because of their similarity to trigonometric functions, not in relation to the circle like normal trig functions, but in relation to the hyperbola, they were called hyperbolic sine, hyperbolic cosine, hyperbolic tangent. In many ways, they are analogous to the trigonometric functions, and they have the same relationship to the hyperbola that the trigonometric functions have to the circle. For this reason, they are collectively called hyperbolic functions, and individually called hyperbolic sine, hyperbolic cosine, etc. Okay, so these are the main functions: sine, hyperbolic sine, and hyperbolic cosine, defined based on these combinations of e to the x and e to the minus x. And then tangent, hyperbolic tangent, hyperbolic cosecant, secant, cotangent are all defined in the same way as the regular trig functions are, right? So tangent, or hyperbolic tangent, is hyperbolic sine divided by hyperbolic cosine. And these are just the inverses of hyperbolic sine, cosine, and tangent. The graphs of hyperbolic sine and cosine can be sketched using graphical addition as in figures 1 and 2. So they're adding, here's 1/2 e to the minus x, here's 1/2 e to the x. You add those two and you get hyperbolic sine. And a similar idea is done for hyperbolic cosine. And then if you divide hyperbolic sine by hyperbolic cosine, you get hyperbolic tangent. Notice that hyperbolic sine has domain all real numbers and range all real numbers. So yeah, you can input any x and you can get output any x. While hyperbolic cosine has domain, so domain all real numbers, but the range is greater than or equal to 1 to infinity. The graph of hyperbolic tangent is shown in figure 3. It has the horizontal asymptotes y is equal to plus or minus 1. So the domain is all real numbers and the range is plus or minus 1. Some of the mathematical uses of hyperbolic functions will be seen in Chapter 7. Applications to science and engineering occur whenever an entity such as light, velocity, electricity, or radioactivity is gradually absorbed or extinguished. For the decay can be represented by hyperbolic functions. Okay. The most famous application is the use of hyperbolic cosine to describe the shape of a hanging wire. It can be proved that if a heavy flexible cable, such as a telephone or power line, is suspended between 2 points at the same height, then it takes the shape of a curve with equation, this equation that's a function of hyperbolic cosine, called a catenary. All right, that's interesting. So if you have a heavy cable, any kind of heavy chain cable, and it's suspended between 2 points, the function that represents this, it involves hyperbolic cosine. This is called a catenary. Another application of hyperbolic functions occurs in the description of ocean waves. The velocity of a water wave with length L moving across a body of water with depth D is modeled by the function. So, okay, the velocity of this ocean wave is modeled using hyperbolic tangent. The velocity is a function of the depth of the wave, or the depth of the ocean underneath the wavelength, and g, which I'm assuming is the gravitational attraction of the Earth. Yeah, g is the acceleration due to gravity. The hyperbolic functions satisfy a number of identities that are similar to well-known trig identities. We list some of them here and leave most of the proofs to the exercises. So here are some hyperbolic identities. They're similar to trig identities, but there are differences. So we know that sine squared plus cosine squared is equal to 1. Here, cosine squared minus sine squared is equal to 1. So there's subtle differences. So in example 1a, they prove this cosine squared or hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Okay, and so how do they do this? Well, they use the definition of hyperbolic cosine and sine, just distribute, simplify, and they prove it. Right, here are the definitions. And then here they prove 1 minus hyperbolic tangent squared is equal to hyperbolic secant squared. They start with this identity, divide by hyperbolic cosine squared, and there you go. The identity proved in example 1a, so the hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, gives a clue to the reason for the name hyperbolic functions. If t is any real number, then the point p cosine t sine t lies on the unit circle. X squared plus y squared is equal to 1. Yeah, exactly. That's how the unit circle works. The coordinates of any point on the unit circle are cosine t sine t, because cosine squared plus sine squared is equal to 1. Yeah, right? That's how the unit circle works with trig functions. Cosine squared plus sine squared is equal to 1. In fact, t can be interpreted as the radian measure of angle POQ in figure 6. Okay? That's what t is, cosine t sine t. For this reason, the trig functions are sometimes called circular functions. Likewise, if t is any real number, then the point p hyperbolic cosine t hyperbolic sine t lies on the right branch of the hyperbola x squared minus y squared is equal to 1, because hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, and hyperbolic cosine of t is greater than or equal to 1. So here's this hyperbola. But if we come back here, they represented this unit circle. This is x squared plus y squared is equal to 1. Okay? And so this is the hyperbola x squared minus y squared is equal to 1. This is the unit circle x squared plus y squared is equal to 1. Now we're talking about cosine of t and sine of t, so this is a different variable t, but this is just, they're just drawing a unit circle here. And then cosine of t is the x coordinate, so like x is a function of t, right? Like you have x of t, y of t. X of t is cosine of t, y of t is sine of t. Here, this is the hyperbola x squared minus y squared is equal to 1. X is a function of t, y is a function of t. So if you plot x of t, y of t, where x of t is hyperbolic cosine of t and y of t is hyperbolic sine of t, that's going to, every one of those points is going to be on this parabola, x squared minus y squared is equal to 1. In a similar way to how if you plot any point cosine t sine of t in the xy plane, yeah, right, x of t, y of t, where x of t is cosine of t, y of t is sine of t, it's going to lie on the unit circle for any value of t. Okay, so this time t does not represent the measure of an angle, so that's kind of, that would have been pretty cool. So like, if we come back here, t, and for this case, t represents the angle measure here in radians. For any t, right, for any t, cosine t sine of t, it's going to be on the unit circle. Right? This is p is x of t, y of t. It's going to be on the unit circle. And also you can take that t and that t equals to the angle in radians, the angle of the point. Right? If the point's here, then you'll have an angle of close to 270, but in radians. Unfortunately, for this hyperbolic cosine of t and hyperbolic sine of t, that t doesn't represent this angle here. But it turns out that t represents twice the area of the shaded hyperbolic sector in figure 7. So t represents twice this area. Just as in the trigonometric case, t represents twice the area of the shaded circular sector. So in this case, t also represents twice the area of this sector. Okay, the derivatives of the hyperbolic functions are easily computed. For example, yeah, you do the derivative, just take the definition of like hyperbolic sine and do the derivative. And so it's interesting, like the derivative of hyperbolic sine is also hyperbolic cosine, just like trig functions, but there are some subtle differences. Like the derivative with respect to x of hyperbolic cosine is not equal to minus sine, it's equal to just sine. So it's similar, but there's subtle differences. Okay, here they're just showing that you can apply the chain rule to hyperbolic functions, just like any, it's like just like any other function. Inverse hyperbolic functions. You can see from figures 1 and 3 that hyperbolic sine and hyperbolic tangent are one-to-one functions, and so they have inverse functions denoted by the inverse of those. Figure 2 shows that hyperbolic cosine is not one-to-one, but when restricted to the domain 0 to infinity, it becomes one-to-one. The inverse hyperbolic cosine function is defined as the inverse of this restricted function. So, yeah, if we come here, so you can see that hyperbolic cosine, it doesn't pass the horizontal line test. But if you restrict the domain of hyperbolic cosine to where it's 0 to infinity, then you can it has an inverse. And so that's what they do here. They're saying that x is restricted to 0 to infinity. That's the domain of this function. The inverse hyperbolic cosine function is defined as the inverse of this restricted function. That's the definition of hyperbolic cosine. It's the inverse of hyperbolic cosine that has domain 0 to infinity. We can sketch the graphs of the inverse hyperbolic sine, cosine, and tangent by using the graphs of the original functions. So remember from algebra how you sketch inverses. It's like it's the mirror it's the mirror of the function about y is equal to x. And so yeah, you can see that the output of inverse hyperbolic cosine is going to be from 1 to infinity, which makes sense. Since the hyperbolic functions are defined in terms of exponential functions, it's not surprising to learn that the inverse hyperbolic functions can be expressed in terms of logarithms. In particular, we have, so since hyperbolic functions are defined in terms of exponential, e to the x, e to the minus x, well, then the inverses you can express with natural logs. Okay, so that's what they do here, right? You just take the inverse of, like for hyperbolic sine, what is the inverse of e to the x minus e to the minus x divided by 2? You just find that inverse in the same way that you find any other inverse, and then you get this. Okay. Okay, now here they give a table of the derivatives of inverse hyperbolic functions. The inverse hyperbolic functions are all differentiable because the hyperbolic functions are differentiable. The formulas in table 6 can be proved either by the method for inverse functions or by differentiating formulas 3, 4, and 5. Yeah, you can just differentiate. That's what they're doing here. They're taking these derivatives. Okay, so that's hyperbolic functions. In the upcoming videos, we'll work some example problems that will help to make sure you have a sound understanding of these concepts.